Hello everybody. Today we're going to derive the idea of impulse momentum principle, and that just explores the idea of momentum. So what we're going to start off with is Newton's second law. So everyone knows Newton's second law. That's just the sum of the forces, the net sum of the forces equals mass times acceleration, and these are vectors, of course. But we can also redefine this definition in terms of momentum. So momentum is actually defined as P equals m times v, and these are vectors as well. So to denote that these are vectors, I'm going to use this tilde sign underneath the variables. And this actually looks very familiar to Newton's second law. So what we can do, since we know that acceleration is the derivative of velocity, we can take the derivative of this equation and set it equal to Newton's second law. So we're going to take the time derivative, and that's represented by this dot. We could say that the time derivative of momentum equals mass times acceleration. So now that we have that, we can actually redefine acceleration in terms of a differential. So we could say that dv dt is equal to acceleration. So now what we could do is separate the variables. So we could say p tilde dot dt equals m dv. And we can also rewrite the time derivative of momentum as the net sum of the forces, since we said the time derivative of momentum actually equals m times a. So what we can do is say the sum of the forces, the vector sum of the forces, times dt equals m dv. So all we have to do now is actually take the integral. So again, we're going to take the integral. So we're going to say this is from t naught to some t final. And we're going to take the integral of this from v naught to v final. So from there, when we take the integral, we could leave this alone and take the integral of this. So we could say mv final minus mv initial equals this right here. So this right here is the idea of impulse. It's also denoted as J, and that's basically a force acting through time. So as long as you have a force acting through time that actually causes a change in momentum, we have to account for it in this equation. For now, I'm going to move this over so we actually get the impulse momentum equation. So we're going to say mv naught plus the integral from t naught to t final, the sum of the forces times dt equals mv final. Notice that these are vectors. So when you use this equation, you are using vector quantities. Now, of course, you could break up the vectors into their x and y components, and if you use each component separately for this equation, so I could say that mvx naught plus t naught tf, the sum of the forces in the x direction, net dt equals mv final x. So you could isolate each component and then just apply this equation, the impulse momentum equation. And then for the impulse, again, you just have to make sure that it's a large enough impulse acting on a very small scale, which actually causes a change in momentum. But technically, any force acting through time is an impulse. But the one criteria that makes it an impulse is that there is actual noticeable change in momentum. Just to use the new notation, we could say that mv naught plus j equals mv final, and that's a vector. Now, let's say that j equals 0, meaning there's no impulses onto the object. Then what we have is v initial equals mv final. And this right here is the conservation of momentum. So that's pretty much it for the impulse momentum equation. The main trick when solving this or deriving this is actually noticing that momentum is the time derivative of momentum is actually equal to the force. So we could use Newton's second law to rewrite this equation in terms of momentum, and then just take integrals of it from a various time with some various change in velocity. And from Newton's second law, what comes out is this idea of impulse, which is basically a force acting through time that causes a change in momentum, or a change in direction, or a change in speed, or even a change in the structure or system. So this right here is actually the linear impulse momentum equation. The word linear just implies that it's going along a path. It's not rotating. Later we'll deal with angular momentum. So right here, this is just linear momentum, not angular. And then if we say that the impulse is equal to 0, what we get is that the conservation of momentum holds true. So that just means the momentum in the beginning is equal to momentum in the at the final state. So that's it for the linear impulse momentum equation and how it's derived. Soon you'll start to notice that this equation right here is probably the only thing you need, because you could derive a lot of physical concepts from this very basic equation. And that's because it's a second order differential equation, which some people forget that it is, because it is not written in terms of derivatives. But once you realize that this is a differential equation, you can actually start solving problems more easily on your own. So that's just my spiel on things, and I'll see you in the next video.